All right. Today we are going to begin the history of the atom and atomic theory. We're going to, if you look at this image that I have on this first slide, we're actually going to start well before Dalton, but he's the first more modern atomic theorist. Eventually we'll move all our way to Schrodinger's electron cloud model. But we're going to start back way before Dalton in ancient Greek times, to who's considered the first philosopher of chemistry and of the atom. And then we're going to slowly make our way to Schrodinger. This video will only cover through Dalton, so from Democritus to Dalton. And then I'll do other videos to get us through all of these models. As you can see, these images are trying to detail what certain scientists thought the atom looked like throughout time. And it changed rapidly within 150 years, but before that, we have to go back to the origin. So that's what we're going to start with today, but I want you to make a note of this image and see how the atom changes throughout time. Okay, so we're going to first just talk about what atomic model is. Okay, you may or may not be familiar with this image of an atom. It's pretty iconic, okay, with that nucleus right in the center with electrons orbiting around. All right, and it's useful. All right, and models are useful to us because they help us visualize and explain unfamiliar things. Okay, so when scientists were trying to understand what we're made up of, what the universe is made up of, they created models in their minds. But in order to explain it to someone else, they needed to have an image or some way to convey that information. And so it's like trying to describe something in a black box. It's something somebody can't see. Somebody can't see. Just like the atom, we can't see the atom with our bare eyes. Okay, they're much, much too small. But we've done other experiments in order to have a sense for what they're made up of and what they can do. The most important thing in science, okay, is this bottom piece. It says a model can be changed as new information is collected. And I hope you really, if you take nothing out of this except that when scientists garnered new information, they changed their idea of the atom and made new models. That's what I really want you to get out of it, is that science is flexible, and when presented with new data and new information that conflicts previous data or information known, that true science progresses and the model will change. And so that's what you want to focus on, is how has the atomic model changed when new evidence has been presented. All right, so we're going to go way back to 400 BC, all right, and where it began that the model of the atom was just, it was a very, very, very tiny billiard ball. Okay, tinier than you can see, but that's what the first scientist, chemist, thought, so to speak. Well, we're going to start with Democritus. He was a Greek philosopher. Back then, they didn't really have scientists, they had philosophers. And he began the search for the description of matter, right? He asked himself, could matter be divided into smaller and smaller pieces forever? Or was there a limit to the number of times a piece could be divided? He wanted to know what was the smallest building block of the universe, right? That's what he philosophized, yes. And he unfortunately lived in an era ruled by other great thinkers, and so his theory was ultimately thrown out. Let's kind of get to his theory here. So his theory is that matter could not be divided into smaller and smaller pieces forever. Eventually, you would reach the atom, the atomos. Okay, this piece would be indivisible. Couldn't get any smaller than that, right? And he named that smallest piece atomos, meaning not to be cut. So the atom, the word atom, comes from this Greek word atomos, meaning not to be cut, or that the atom cannot be cut. We know that's not true now, but that's what he philosophized 2,400 years ago. So to Democritus, this moving image, atoms were small. Okay, they were hard particles, and they were all made up of the same material, but were different shapes and sizes. He also speculated that there were infinite in number and always moving in, and capable of joining together in infinite ways. That's kind of how he postulated atoms to be. Not a bad image for somebody who was living in the ancient times. However, Democritus's theory was ignored and forgotten for more than 2,000 years. And if you just take a moment to think about like how science could have progressed differently if we had ignored him for 2,000 years, well, I'll let you ponder that. So why though? Why was his theory left by the wayside? Okay, unfortunately for Democritus, he lived in the time of Aristotle, okay, and Plato. And those philosophers were much more respected, and ultimately their theories on how the world was made up prevailed. Okay, so Aristotle and Plato favored that everything in the universe was made up of one of the four elements: air, fire, water, earth. Okay, and that different combinations of these. If you ever played the game Alchemy on your smartphone, you'll know that it starts with these four elements, and you can seemingly make everything from them. This is not true. However, because Aristotle was kind of the law of the land, and so to speak, and people took him more seriously, people believed him. Now, there's always a small fraction of people who thought Democritus was right, but if I had, you know, anything to say to Aristotle, it would have been like, maybe take heedance from others more so than just believing your own way. Again, all right, if we look at this next slide, this timeline of atomic theory, it's depressing to me, okay? So here is the Greek model, Democritus's theory. This is when he theorized that the atom was the smallest building block, okay? And then Aristotle's four elements is ultimately what ruled the day for 2,200 years, okay? So here is when Dalton, our next, one of our next, he's the next scientist to go back to what Democritus stated, that the atom is the smallest building block of matter. This is the Middle Ages, the Dark Ages, okay? It wasn't until the Enlightenment period when people started to question that maybe we were wrong about how we think about the Earth. And what is frustrating, or rather exciting, is that like after Dalton proposed this theory, science really took off. As you can see here, after his model, okay, it's less than a century later, Thomson's model that we'll learn about, then Rutherford, then Bohr, and then ultimately the wave modern model. We'll get to Schrodinger here last, but this happened in like 1926. So less than 150 years after Dalton, we progressed so rapidly. And if you think about how science has changed even in the last 100 years, it's crazy to think about that. If we had started back here and took Democritus's theory seriously and developed a real science, where would we be today? Again, just ponder that in your late night wanderings of the world. So that's Democritus. Next, we're going to cover not someone on the timeline, but he's important. Antoine Lavoisier. Okay, he's a Frenchman, very famous one. He is known as the father of modern chemistry. Okay, so Democritus is like ancient chemistry or ancient scientific thought. But Lavoisier, he lived in the 1700s, and he was a Frenchman, and he was very interested in the world around him. And he was the first person to generate a list of 33 elements, and he made a textbook. He was also wealthy, so he had some privilege, but he used it to further scientific progress, and so we can thank him for that. He had hundreds of people working for him who conducted experiments and really paved the way for scientific experimenting back in the 1800s. You can love him or hate him, but he's the reason we have the metric system. He really believed that we needed to have um, worldwide standards for measurement so that scientists could compare their work. So he devised the metric system, that 10-base system that is still used today. It's been changed somewhat, but the basics was from him. Unfortunately for us, he was a tax collector as well, his other side, and he was guillotined during the French Revolution. So he had a painful, awful death, but not before putting out a lot of useful information. So he discovered or proposed the law of conservation of mass, okay, which states in a chemical reaction mass is neither created or destroyed. I know you've heard that many times, but I want to kind of get into a little bit how he proposed this in some of the very cool experiments that he did back in the day. So here's a little bit, it's not really how he fully conducted the experiment. He used much, different equipment, but just go with me here. So he had on a balance, okay, like one of those teeter-totter balances, he had a mass of something equal and opposite to an amount of tin in a sealed glass vessel. All right, and he heated it over several days. So he put a piece of tin, he sealed it so that nothing could get in, nothing would be able to get out of this vessel. He weighed it, heated it for a couple of days. Over that time, he noticed that a quantity of white powder, like the contents within the vessel, were changing. Okay, and so it wasn't this nice piece of tin anymore. There was some white powder, but the mass of that container did not change. So obviously some kind of chemical reaction occurred. Stuff doesn't just spontaneously turn to powder. And so, however, he couldn't explain it by a change in mass. So when he opened the flask, being the careful scientist that he was, he did notice that air rushed in. Okay, and then after, when he weighed the flask again, he found that the weight had increased. So after doing all these careful observations and repeating this experiment multiple times, he came up with some conclusions. So here are some of the conclusions he drew from this brilliant scientific mind. He concluded that tin, on being heated, combined with something in the air. There was something present in that flask that he couldn't see, but yet he concluded that there must be something in there that reacted with the piece of tin metal. And that is what the white powder was formed of. Okay, heating it produced no change in the total mass because the atoms were just rearranging within that flask. Okay, but when the flask was opened, he assumed air rushed in and took the place of the substance which had combined with the tin, and now the flask weighed more because of the additional air that entered. So if you imagine as that this was his piece of tin, and these were the pieces, it ended up being oxygen. I'll show you in the next slide. Okay, now these would have been floating around, but for the sake of this image, okay, they then rearranged so his substance looked different over time while heating it, but yet the mass didn't change because the atoms were just rearranged. So you can't create matter, you can't destroy matter, but matter can rearrange itself, and that's a chemical reaction. He was the first one to kind of prove this and move scientific theory forward. Now, I have this slide. I'm not going to read it. If you are really interested in a little bit more of Lavoisier's experiments, you can pause this video, read this slide. I'll do the next for the next one. So you'd pause it now. Okay, I'm going to go to the next slide. I have tons of stuff on Lavoisier. Again, you would pause it and read this to get a little bit more insight on how he conducted his experiments. Okay, but I'm going to move on. So if you want to do that, go back, pause the video, and read about more of Lavoisier's amazing scientific work. We're going to finish up this video with Dalton. So Dalton, in the early 1800s, okay, he was an English chemist. He was actually a school teacher, but he He had a very scientific, keenly acute mind, and he performed a number of experiments that ultimately led to the acceptance of the ideas of atoms. So a little bit about Dalton. He was a school teacher, like I said, but he also, for 57 years, he studied and recorded the weather. And he got a lot of insight into present-day meteorology. In that, in his notes, he became fascinated with the idea of gases in the wind and in the atmosphere. And through his study of gases, he came to draw some conclusions about what um, the world was made up of. So here's what he ultimately decided. Here's his theory. This is in your book, something you definitely want to know and become familiar with, as well as the law of multiple proportions and the law of definite proportions. I'm not outlining them in this video, but they are in your book, and I would expect you to know them and have an idea for how they relate to Dalton's atomic theory. Okay, so he has basically 5 postulates. The first one being that he deduced that all elements are composed of atoms, right? And we learned about Lavoisier. He proved that there were 33 elements, and he had characterized them at this point. So he deduced that atoms are indivisible and indestructible particles. Okay, you can't go anything smaller than an atom, is what Dalton deduced. He also deduced that atoms of the same element are exactly alike. So all hydrogen atoms are the same of each other, and all helium atoms are the same. Okay, there were no differences of one specific element. He also stated that the atoms of different elements are different in their physical and chemical properties. So he said oxygen is different than tin, has different physical properties. One's a solid, one's a gas, has different chemical properties. They react differently. Okay, and if you read a little bit more about Lavoisier's experiments, you know something about how mercury and oxygen reacted and how oxygen will burn. You need, in order to burn a fire, there needs to be oxygen, but if you have pure oxygen, stuff is going to burn much more, much better than if you don't have pure oxygen present. So like different atoms have different physical and chemical properties, which we did talk about chemical and physical properties in the last unit. All right. His fourth postulate is that atoms only combine in small whole number ratios. Okay, so like water, if you see here, this is trying to show hydrogen atom, oxygen atoms, and this is making water, H2O. Okay, compounds can only form in whole number ratios. You can't have half of a hydrogen atom. You can't have 2/3 of an. You can have 1, 2, 3, the whole numbers. So you can react molecules and create compounds in different ratios, but they are always whole numbers. And his fifth postulate is that, and he kind of expanded Lavoisier's, but in chemical reactions, atoms can be combined, separated, or rearranged, but they can never be created or destroyed. So Dalton paved the way for modern chemistry as well as Lavoisier. Of his 5 postulates, these 3 are still true today. The first 2, okay, we know that atoms can be broken down into smaller components, protons, neutrons, electrons, as well as there's more than that, but that's what we're going to study in chemistry. And also, we just learned that atoms of the same element are not exactly alike. There's a thing called an isotope. So you can have different isotopes of atoms, and they have different properties. So not atoms of the same element are exactly alike. Are they similar? Oh yeah. But isotopes make them slightly different because they have different numbers of neutrons, and then therefore slightly different properties. But for the most part, you can say this is still true, however, not 100%. The rest of these are still definitely true. And for Dalton to propose this in the 1800s is nothing short of a miracle. So we're going to end this video today. His theory became one of the foundations of modern chemistry, and our next video that you watch is going to continue the story there. Hope this helped and is a good resource for you in the history of the atom, part 1.